check. Okay, so today the plan was to talk a little bit more about these bell states. I still haven't written out all of them for you. So let's start by doing that. And then during the tutorial, this question came up as to how one might actually prepare these states. How does one realize these kind of entangled states? In particular, we were talking about the Schmidt form. And then we saw how if you do local unitaries, you don't change the entanglement content of the state. So the question then becomes, how does one actually create entanglement in some sense? What is the resource required for us to be able to prepare these bell states? And then what are they useful for? What are the kind of nice, cool things that we can do if one is able to prepare these kind of entangled states, right? So let me start by writing down a set of 4 states. I wrote this during the tutorial session last evening, but maybe everyone was not here. So I'm going to label them in this way, as I said. So there is this. No, I keep making this notational mistake, so you'll see why I keep bothering with this notation of 0, 1, 1, 0, etc. So the point is you have states which are exactly correlated, so this is all written in the sigma z basis, as I told you yesterday. There are 4 states, 2 of which are exactly correlated in the z basis outcome, and the only difference between them is the phase. So these are both perfectly correlated in the, as far as the z basis measurements are concerned, in the 2 systems, and the only difference being this relative phase, and these 2 are perfectly anti-correlated, again the only difference being this relative phase. And then we saw, at least during the tutorial, I asked you to check that this is a set of 4 orthonormal states. So this should then give us an orthonormal basis for this 2-qubit space that we are working in, right? Now we already wrote down different basis for this space of 2 qubits. So recall that we already wrote down what I'm going to call a product basis, right, which is simply the 0, 0, 0, 1, 1, 0, 1, 1. And now this is actually an entangled basis, right? This is a set of 4 entangled states. So by now you recognize that these are all in Schmidt form. They are indeed maximally entangled. They have the equal superposition between these two states, right? And if you, by now if you're familiar with the reduced density matrix, you should be able to see that all of them, the reduced density matrices are the maximally mixed states. So this is a set of 4 maximally entangled states, which forms a basis for this space of 2 qubits. And then here I have these 4 product states, which also form a basis for the 2 qubit space. So then I know that I can transform from one basis to another via unitary transformation, right? So there must exist a unitary transformation that takes me from this basis to that, right? Now, what kind of unitary transformations can I think of on this 2 qubit space? So we call them A and B or something, right? So, and we discussed this again briefly last evening. So if I were to apply a unitary only on subsystem A and a unitary transformation separately on subsystem B, this is what I would call a product of local unitaries, right? And my intuition should be that this kind of an operation is not going to help me go back and forth between these pair of bases, right? When I have a product state, so you can see this, so I apply this on any product state of this bipartite system, I'm going to get some other product state. I'm not going to get an entangled state like this. Is that clear? So in order to prepare an entangled state starting from a product state, I need a class of unitaries which are not of this product form, okay? And in the literature, these go by the name of entangling unitaries. So I have to start thinking about so what would be an example of an entangling unitary? And I know many of you may not be familiar with this kind of quantum circuit picture that we draw, but hopefully it's intuitive enough. I'm going to draw some pictures which are what we call quantum circuits. It's easier to understand this idea that way. So what do I mean by a quantum circuit? So I'm going to say that this operation where I applied a local unitary on each subsystem. So I'm going to draw 2 lines and say this is subsystem A and this is subsystem B, okay? And let's say the arrow of time flows from left to right. And I'm going to put boxes to represent unitary transformations that I'm doing along the way. So this is basically a circuit like this, right? It's a picture like this where I'm doing something to subsystem A and something else to subsystem B completely independent of each other, right? And this is only going to take product states to product states. If I have a maximally entangled state, we did this little exercise last evening, you do local unitaries on a maximally entangled state, you transform it to another maximally entangled state. So the entanglement of a state, I know I'm just using examples to say this, but can be formally shown that the entanglement content of a state cannot increase or decrease under local unitary transformations. So to contrast with this, what I need to do is a joint unitary on A and B. And I'm going to tell you what kind of joint unitary we need in this case as an example of what kind of operations can be thought of as entangling operations. So the unitary that we are going to use is it's an important operation in quantum computation and quantum information. It's something that we call a C0, okay, which stands for a controlled NOT gate, a controlled NOT operation, and NOT representing in the computational sense a bit flip, right? So in the quantum case, what would I think of as a NOT operation? Assuming we're constantly working with the Z basis, then a NOT operation is something that is going to flip this label that's sitting inside this, right? So if ket 0, which we said is the +1 eigenstate of the sigma Z operator, transforming that to ket 1, which is the -1 eigenstate of the sigma Z operator, and vice versa. So if I do this transformation in a unitary way, of course I know if I apply the unitary, the inverse of the unitary, I'm going to get back here, right? And which is the operation that is going to toggle between the plus and minus eigenstates of the sigma Z operator? The sigma X operator. So you know that the sigma X operator is like a quantum NOT operation. Maybe I use the word gate, okay? With the understanding that my ket 0 is like a logical 0 state and a ket 1 is a logical 1 state. In a computational sense, this is like doing what we think of as a NOT gate, right? So the sigma X essentially functions as a quantum NOT gate. Now this sort of non-local or entangling operation I want to think about, I'm going to write this out algebraically and then we'll see what this does. It's a controlled NOT. Okay, so there are 2 qubits now. I want to create some correlation between them, right? The way I create this correlation is by controlling what happens to the second system based on the state of the first system. Okay, so I use the first system as a control, and based on the state of the first system, I do something to the second system. How do I actually write this down? So what am I doing if I try to break open this box? So I've described in words what I want to do. Specifically, let's say I want to do the following. If my first system is in, so these are all 2-dimensional. So if my first system is in state 0, I want the second system to be left untouched. And if my first system is in state 1, I want to apply this sigma X operation on the second system. What does this actually entail? It says, okay, maybe one way to do this is measure the state of the first system. Okay? Measure the first system, and depending on that, you do something to the second system. Will that entangle the 2 systems? What do you think? When you measure the first system, you're actually collapsing the state of the first system. So if your first system was in a superposition state, you've actually broken that. So that's not even a unitary transformation, right? So I cannot do this operation by looking at one system and then doing something to the other in the quantum case. So I have to find a cleverer way of doing this, and the way that we do this is think of a projection onto ket 0 on the first system. If it is 0, you do nothing to the second system, but this operation happens in combination with the other operation, where if it's a 1 on the first system, then it's a sigma X on the second system. Now in doing this, you have not really measured the first qubit. You have applied a projection operator to the first qubit and something else to the second qubit, another projection operator to the first qubit and something else to the second qubit, in such a way that this combination is actually unitary. So you could maybe check just from this algebraic form that this is unitary, or one can actually write down. So this is a 2-qubit operation, so it has to be a 4 cross 4 matrix. So one can actually write down this 4 cross 4 matrix, and it's useful to do that because I'm going to contrast it with, and it's also good to maybe see how this tensor product structure comes into play. So let's try to write this out. So how would you check if this is unitary or not? Well, you just do and see if this is identity, right? And I'm sure you can check that and verify this very quickly. But how do I write down a matrix form for this? Let me keep the Bell states there. So I think during the first lecture yesterday afternoon, the tensor product was actually discussed and used multiple times. So you all know how to do this tensor product. So let me write this out. So what does this C0 operation look like? The projection on 0 is simply this matrix, right? And the projection on 1 is this matrix. Oops. So this gives me a matrix of this form. Yeah? This is my 4 cross 4 matrix, and indeed you see that if you think of the basis states, then these correspond to the ones where the first qubit is in 0, and these corresponds to the one where the first qubit is in state 1, and in this second part of the block you have a sigma x, in the first part you have an identity, and these two parts do not mix, so there's nothing here, right? So this achieves what we want. Note that this is not the same as doing identity in A and sigma x in B. What did I do? I broke down the identity operator as a projection on 0 and a projection on 1, right? That's what this is. If I sum these two, I get identity operator on the first qubit. But I have broken it down into a pair of projectors, and each one I have coupled to some other operation in system B and then combined them. So what I've written is a combination of local operations, a combination of tensor products, and not a single tensor product. Can you quickly work out what this matrix is and tell me? This is also a 4 cross 4 matrix. Sorry? What does that mean? Just so you basically have this, right? Yeah, okay, good. So the C0 operation is not identity tensor sigma x, okay, which will give you this matrix, which is a completely factorizable unitary. Okay, this is also a bipartite unitary, which is completely factorizable into a local operation on 1 and 2. This is truly a non-local operation, and this presumably can help us realize an entangled state. Okay, so this is one of the ingredients that goes into realizing an entangled state, because just with this operation it's still not clear what's happening, no? Because it's still only taking product states to product states. What is the action of this on the standard basis, the 0-1 basis? It's easy to see that what this is going to do is exactly what I described in words. It's going to take, so it's going to do this, right? 0, 0, nothing happens, 0, 1. So everywhere we assume that this is A and B, okay? Nothing happens, but 1, 0 will become 1, 1, and 1, 1 will become 1, 0. Yeah? So this does nothing to generate entanglement on product states. The other crucial ingredient that you need here is superposition. So you start with a superposition state and then apply this entangling unitary and see what happens. So that's what we're going to do. Now the question is, all of these, as you can see, are in some sense uniform superpositions, equal superpositions. So do we know of an operation that's going to create a uniform superposition of 0 and 1? Yeah, I'm sure some of you know this. Sorry? Hadamard. So this is what is called a Hadamard operation. It's something all of us are familiar with in a different way. See, what do I want to do? I want to make 0, let's say, into a uniform superposition of 0 and 1. But this is nothing but a sigma x eigenstate, right? And if I want to do this in a unitary fashion, then I better do something to 1 so that it maps orthogonal states to orthogonal states. So essentially, I want a transformation that goes from the sigma z basis to the sigma x basis. And you can work out that this transformation is a 2 cross 2 unitary matrix which goes by the name of the Hadamard, which looks like this. So I hope I can erase this part. So once this operation is written out, it's easy to write down this matrix in the same basis, right? It looks like, so H looks like 1 over root 2, 1, 1, 1 minus 1, okay? And this is again a very crucial ingredient in quantum algorithms and such, because you can see that this multiple applications of this on, let's say, multiple qubits is going to generate for me nice uniform superposition states of multiple qubits, which essentially serves as a starting point for many quantum algorithms, okay? After all, what is quantum computation doing? It's exploiting the power of superposition and then, of course, entanglement, right? So the first step is always to prepare a nice superposition state, and this Hadamard operation helps us do exactly that. All right, so now I have the two ingredients that I need to prepare these states. So this is what, so remember this kind of circuit picture that I drew. So this is what happens. I have these two systems, A and B. I prepare one of them in a superposition by applying this transformation, okay? Of course, I leave it to you to check it's unitary. Not only is it unitary, its inverse is the same. In the sense, the same operation is going to take you back from sigma x back to sigma z, okay? And then I'm going to apply this non-local gate, the C naught. There is a sort of symbol that we use for this. So maybe let me just use that, okay? Basically, this is the C naught transformation between A and B, okay? And now I'll work out one example case and then leave it to you to work out the rest. So let's say I start with a tensor product state, okay? I start with a product state between A and B. So now, like I said, the arrow of time flows this way. So I first apply this superposing, the gate that prepares the superposition, and then I apply this non-local transformation. So let's try to work out what happens. So I'm going to draw very soon a bigger circuit to show this teleportation. So let's try to see how do we analyze these circuits. So let's see what happens here. This is just 0 tensor 0 with Hadamard tensor identity, right? And Hadamard takes 0 to the uniform superposition of 0 and 1. And nothing happens to B in the first step, okay? And maybe I use a different color for this. What happens at the end, once you apply the so I'm going to write this state as some capital psi AB. So that is basically the action of the C naught on this state, right? The tensor product is linear, so I expand this. So I have 0A, 0B, tensor, I'm sorry, plus 1A, 0B, okay? And I have this 1 over root 2. And now the action of the C naught becomes something non-trivial, okay? Note that even until this step, I'm not entangled. I have not entangled anything because this is just ket plus in A, tensor 0 in B, right? Product state. But now the action of the C naught is doing what we said it should do, which is it's somehow reading off the first qubit without really measuring it and doing something to the second qubit based on what the state of the first qubit is, okay? Because what happens now, the 0, 0, remember, remains unchanged, but the 1, 0 now becomes 1, 1. And so you have the first Bell state that we wrote down here, okay? So both these ingredients are important. Without the superposition, I wouldn't have been able to transform this product state into an entangled state. And also, I need this entangling operation which engineers correlations between these two systems, right? So now you can start with different product states here from the standard basis, 0, 1, 1, 0, 1, 1, etc. And you will realize this set of 4 states, and that's why I put these labels on them to kind of make this association. So what is this unitary transformation that is transforming these two bases? It is this complete box. It is this complete combination of Hadamard tensor identity followed by a C naught. That is some other 4 cross 4 matrix, whatever it is. That is my matrix which transforms from a product basis to an entangling basis. Now, this whole thing is unitary, which means I can do this operation completely in reverse, which means I do this C naught first, and then I do the Hadamard, then I'm doing exactly the reverse. I disentangle the systems, I undo the superposition, and I come back to my original product basis, which is 0, 0, 0, 1, 1, 0, 1, 1. Okay? So this is how one would think of preparing the Bell states in a sort of mathematical way. Well, physically, how are Bell states prepared? So as you know, most of these experiments that we do, which use these kind of entangled states, are entangled photon pairs, right? And we have labs here which actually prepare these entangled photon pairs using a process called parametric down conversion, right? So you need some nonlinear interaction in a crystal which causes this angular momentum degree of freedom to essentially get correlated, and then the photons that come out are entangled in the polarization basis. In fact, if one were to model this nonlinearity, for people who know a little bit of quantum optics, I don't know, there's something called Kerr nonlinearity, and if you were to model that interaction and bring it down to bar tracks, it looks something like a C naught operation. So you can think of this C naught operation as being the sort of matrix counterpart of that nonlinearity which you need in a physical system in order to get entangled states.
All these processes are reversible.
Yes?
In quantum information, do we use irreversible processes also somewhere?
So as a quantum information processing person, I would like to stick with only reversible operations, okay? Because that means that I'm working within closed quantum systems. And I would like to work with closed quantum systems because I have maximum control over them. But unfortunately, the real world is not a closed quantum system. And because of interactions which you cannot prevent, and typically with a system which is much larger, like an environment or a bath, you have irreversible processes that come in. But even before that, if I want to do this quantum information processing or computing, I get these entangled states, I do something to them, and finally I have to measure. And the act of measurement is again something that is irreversible. So I would like my computation to proceed in a very deterministic unitary fashion, which is fully reversible, right? But the irreversibility comes in once you measure, because finally I'm reading in and out in a classical way. So I have to read out. I need that classical information back. And for that, I need an irreversible process. And then, of course, there is decoherence and all that, which causes irreversibility, right? Yeah.
I was just wondering, how should we compute this, create this C0 gate in experiments?
So one way, for example, I think again here there are labs which do Rydberg atoms. So there is something called a Rydberg blockage, right? Where you bring in these two Rydberg atoms in proximity together. So what is it saying? It is saying that out of the set of all possible states, so imagine each Rydberg atom as a two-level system, and then you're saying that out of all possible states, there are only certain states that get picked, right? And so one way to do this is to actually just bring two Rydberg atoms close together, and then there's something called a Rydberg blockage which happens, right? Which causes a C0 gate. But in a very matrix sense, you can think about just doing this, right? You can think about this itself as a matrix transformation which you engineer on a many-body system. It's a sigma x and identity, and with just projections onto 0 and 1.
Matrix transformation, I understand mathematics.
Yeah. So the Rydberg blockage is one such. I'm not an expert on that, but maybe you can read up on that if, yeah.
My first question is regarding, can you repeat what you said about the reversibility of this gate?
No, so they're all unitary transformations. So they're all reversible. This is a combination of two unitary operations. So I should be, so when I say reversible, it means that what is a unitary transformation? In what sense is it reversible? So U inverse is U adjoint, right? It turns out that in this case, U inverse is the same as U in both these cases. So maybe I skipped that step, maybe that's why it's confusing to you. So I can simply apply again. So I have the entangled state here. I simply apply this again, and I apply this again, which means I sort of repeat the circuit, except I do it in the reverse order. So I first put the C0 block, then I put the Hadamard, and then I'll get back this state. Because in both the cases, the inverse is the same as the matrix itself.
Wasn't it like, maybe I misunderstood, but you said like the unitaries cannot change entanglement?
Local unitaries. Local unitaries. If I was only allowed to do one unitary here and one unitary here and not be able to interact them in any way, right? Then. So by the way, there's a Hamiltonian way of engineering a C0, right? Because think of this as a unitary transformation. Now there must be some e to the I h, let me put some, I'm going to put some parameter theta here instead of time, okay? So you know that there must be a Hermitian matrix with a real parameter here. Normally it is time. In this case, I'm going to make it an angle parameter, okay? Such that I realize this U, right? So with every U, I should be able to associate this. So this is one way. And in fact, this turns out to be a product of Pauli matrices. So I can, in fact, engineer the C0 using a Pauli Hamiltonian, okay?
You said something about the parametric transformation.
Yeah.
As much as I understand it, in that parametric transformation, that photon gets transferred.
Yeah.
And two photons, this energy somehow
Yeah. Yeah. Yeah.
they get created.
Yeah.
Those are active.
Yeah. Yeah.
But how is that like this after C0?
So if you think of that as an interaction between photon and vacuum, okay? And then you work in this two-dimensional system which simply has single photon and vacuum, okay? or a pair of photons, restrict your Fock basis to only two photon number states, okay? Then you again have a matrix that you can write down which looks like the C naught. You don't take into account all the higher modes, right? But you think of it as photon and vacuum, yeah. Okay, all right. So what can we do with entangled states? Any more questions on this? So there is a whole theory of entangling unitaries and so on, which I'm not getting into. I've just shown you an example of such a unitary transformation, right? So I don't know if people followed the, so this Google experiment, right? I don't know, are people aware of this Google experiment that happened a couple of years ago? Quantum supremacy, quantum advantage, yes? No? So all these experiments which claim to show quantum advantage or quantum supremacy in some way, they rely on these kind of non-local or entangling unitaries. Usually these experiments, one can think of them as a many-body circuit if you wish. They have like some tens of qubits, like the Google chip has 72 qubits. So it's a 72-partite quantum system, if you will. And they sort of, so these are sometimes called these brick wall circuits. So maybe I'll just quickly show what I mean by this. So I just want to point out that these kind of gates are required in order to even make what one may think of as quantum simulators and so on. So you think of many, many qubits, and you think of basically applying in some random fashion, okay, these non-local or entangling gates between pairs of them, okay? So these are, like I said, sometimes called brick wall circuits. And you intersperse this also, like I said, it's not just enough to have entangling gates. You need the single qubit operations. You need the local operations also, so as to constantly have these superpositions going on, right? So they also intersperse this with some local, so I'm going to call these as R, essentially random local unitaries, okay? And this kind of a, so this is what is many times called a random quantum circuit. This kind of a random quantum circuit model is one of the sort of easiest candidates where you can show quantum advantage, okay? So just for those of you who know of this Google experiment, this is what they do, and they fix a particular non-local gate in their interaction, which happens to be the C naught in their case, right? But you could think of different such operations which you fix. Where you fix an entangling operation, you introduce randomness by the choice of systems that you pick on which you do this entangling operation. You introduce additional randomness locally on each qubit by doing local random unitaries, and then you have a phenomenon which you cannot easily reproduce in a classical way. Yeah.
Can you give example of quantum advantage?
Sorry?
Can you give an example of quantum advantage?
The example is just this. You prepare this kind of a circuit, and you generate a probability distribution at the end by measuring in the standard basis, okay? And then you ask, what is the complexity, classical complexity of realizing a random string with this degree of randomness? And basically you will outdo the classical circuit, yeah? Okay, last, yeah.
What do you mean by complexity of the resulting distribution? Like just the entropy or what?
No, how random is your string here?
Ah.
And what is the sort of sampling complexity in a classical sense? So you have to sample over some probability distribution in order to get this random string. And there's a sampling complexity associated with that.
In any non-local unitary, we approximated with these like like unitaries which no-local unitaries which acts on 2 qubits, and then like some combination.
So you're asking whether I can break down a unitary like this say A, B, C, D, etc. Let's say it's some n qubit unitary. Can I break this down in terms of just 2 qubit unitaries and single qubit unitaries? And the answer is indeed yes. This statement that you can break down any D cross D unitary purely in terms of single qubit gates and 2 qubit, a single 2 qubit unitary in fact, is the statement of universality of quantum computation. So if I want to think about quantum computation, what is it? It simply involves unitaries of this kind, right? But now I don't have a single qubit, I don't have 2 qubits, I have some n qubits. So this is in general some D cross D unitary matrix that I want to realize. But if I want to think of this as a computational model, I must be able to identify a set of basic operations in terms of which I'm able to realize an arbitrary D cross D operation, okay? And the answer is yes. So if just using, so let me just write this statement here. So any D cross D unitary transformation can be realized using just the C naught and some set of single qubit operations. I'm not writing down what they are. There is in fact a very precise set, okay? So you're essentially saying that you can approximate this continuous parameter group using a discrete set of operations. Of course, it's not going to be exact. There is going to be an approximation, but to arbitrary degree of approximation, you can actually realize any D cross D unitary using this. So this statement goes by the name of the Solovay-Kitaev theorem. It's a very beautiful result in quantum computation. Yeah, I would refer you to either the Preskill notes or the book by Nielsen and Chuang for a nice proof of this, okay? So yes, so this also tells you that the C naught is a crucial ingredient for quantum computation or quantum information processing in general. All right. Okay, so let's see what we can do with the Bell states. So of course, one fancy thing which you can do is this idea of teleportation, right? I'm not going to again do the detailed circuit, the detailed sort of calculation for that, but just show you what one is doing in this. Okay, so the task of teleportation can be stated as follows. You have two parties who share some entanglement. Someone gives one of these parties, A, an arbitrary single qubit quantum state. So I'm stating this only for qubits. The idea can be generalized, of course. And the task is for A to communicate this state to B. They are spatially separated. The only resources they have are, so I'm going to draw two lines here to say that this is a classical communication channel, okay? Meaning WhatsApp, a telephone line, whatever, right? So they have a classical communication channel. They can WhatsApp each other. But they don't have a mechanism by which they can actually send across this quantum state. But somehow they have a source of entangled photons through which someone is sending them pairs of entangled photons. Okay? So this idea is basically to say that they have, and in this whole scheme, it's actually enough to have just one entangled pair to do this task. Okay? So one entangled state is often called an E bit. Okay? And then I have classical bits, which are just bits, but I'm going to call them C bits. So the question is, can I use one entangled bit, some classical bits, I don't know how many, to actually communicate one qubit? Okay? Now, one thing you could suggest that A does, instead of doing some fancy teleportation, etc., and you may ask, why do you even need the entangled bit? Cannot A just measure the state? Cannot A just measure, read out the state and send that across to B? Yes, no? Yes, so how many measurements does A have to do? Just one measurement? Okay, so what is psi? Psi is, like I said, an arbitrary single qubit state, which, just Jaikumar is not here today, as he would say, someone has put it in a box and given it to A. Okay? A was not involved in the making of this. Was a PhD student. Sorry. Okay? So this is all the information that A has, that it is some alpha 0 plus beta 1. Now, how many measurements do you need? So what do you need? What does A need to get? A need to know what is alpha and what is beta. PhD student has gone off to a trek in the Himalayas. No idea what A and alpha and beta are. But A has the box, and just one box. Even to get either alpha or beta, you realize that when I do a measurement on a quantum state, each measurement gives me one outcome. Each time A is going to get either 0 or 1. So A needs many copies of the state, which then A has to repeatedly measure in the 0-1 basis, collect statistics, but even after all that hard work, A gets only the probability distribution, which is not alpha beta, that is mod alpha squared and mod beta squared. So there's still phase information out there. Okay? So yes, there are schemes. So this whole question of how do you determine an unknown quantum state is called quantum tomography. Oops. So that in itself is an interesting field of research. What is the smallest number of measurements that you need to perform? So it turns out that it is not enough for A to just measure in the sigma z basis, because then A is only going to get mod alpha squared and mod beta squared. How does A get a handle of this phase information? So A will have to rotate, do sigma x measurement on some copies of the state, and so on and so forth. So this is an expensive process. Even today, if one has used any of these IBM quantum hardware and things like that, you'll realize that tomography is in fact the most expensive step of the entire thing, right? Because you need to run this 1,000 times. You need to do this 1,000 times to get meaningful statistics out of it, and not just in one basis, but in multiple bases. Okay, so this is not something that A wants to do. So that is the reason, that is where this sharing this entangled state helps. You don't need to know what the state is. You don't need to measure, do tomography, identify the state, etc. You simply need to perform certain operations, unitary transformations, involving this state and the one half of the entangled state that A has. And just by performing such a joint operation between this unknown qubit and her half of the entangled state, A is able to collapse B's state in such a way that B can then simply realize the same state in his lab. Yeah. Psi is a single qubit state. This is an entangled pair. So I'm drawing these two dots here to say that this is a bipartite state, right? One half of which A shares and one half of which B has. Okay? Right? So how does this magic happen? Huh? So, okay, yeah. So After A does whatever joint operation on the unknown qubit and her half of the entangled state, she has to do a measurement and communicate some classical information to B. This again goes back to some of the more philosophical questions we were asking yesterday about, is there some faster than light phenomenon happening when one is using pairs of entangled states and saying that these outcomes are correlated. So if A did not do this classical communication, then although the state in B's lab has reached this state, B does not have access to it until these classical bits of communication have been communicated. So thanks. So this is a very crucial step of the teleportation protocol, as I will just say, which says that it's all very normal stuff, nothing spooky happening, but it's just a very clever way of manipulating this resource that we have called entanglement. Yeah? It means you're sharing one pair of entangled state, one pair. You're sharing one entangled state. So let me just say that this is one entangled state. So it's just a convention that quantum information guys came up with to talk about these resources. So it's one entangled state. We think of that as one E bit. It's actually, remember, 2 qubits, actually, right? One entangled state is a pair of qubits, one of which is sitting in this lab and the other is sitting in the other lab. Yeah, so now we'll just see how many classical bits have to be communicated. And then you'll see why this is so much more nicer than A having to have 1,000 copies of the state, measure, and then send that classical information across. Okay? Yeah, C bits is just bits, classical bits, like I said. Okay, let me just make sure I don't make a mistake in drawing this picture. Okay, so I'm now going to divide up A's system because A is dealing with 2 qubits in her own lab. So I'm going to call one of these as A1 and the other one as A2. So I'm going to call this as A2 and this unknown state as A1, okay? So there are 3 quantum systems in play here now, okay? There is A1, which is the, by unknown I just mean an arbitrary single qubit state about which A need not have any knowledge, okay? That is A1. Then A2 is the qubit which is sitting in an entangled state with the qubit of B, and let's say this is just the beta 00 state, 00 plus 11 over root 2. Now it turns out that all A needs to do is to first entangle these 2 qubits in her lab, okay? So she needs to do a C0, and this is the same operation which I showed there. She needs to do a C0 and entangle the 2 qubits in her lab. The one in the box which was given to her and the 1/2 of the entangled state that she has. And then she has to do a single qubit Hadamard on the A1 qubit, and then she has to measure, so we usually draw this to say that these 2 qubits are measured. B of course does nothing until now, and then having measured, she now uses her WhatsApp to communicate the measurement outcome to B. Now, how many bits does she communicate? 2, right? So this is just exactly 2 classical bits. You can just pause a moment here and imagine, suppose I actually wanted to do tomography and communicate. See, so I can measure a quantum state. I can essentially get hold of alpha and beta in some way. That is classical information which I can communicate, which A could communicate. How much classical information is that? Is that something that you can contain in 2 bits? what is the classical information that has to be communicated? It is a pair of complex numbers. You can, of course, simplify this. I mean, this is a normalized state, so mod alpha squared plus mod beta squared is 1, etc. You can bring this down to 2 real parameters. But it's 2 real numbers which have to be communicated. Okay? So the complexity of that is typically much larger than just communicating a pair of classical bits, which is all that has to happen in the teleportation scheme. Yeah? That's a separate problem. So here's a homework problem. I have an arbitrary single qubit, single quantum state of 2 dimensions. How many real parameters do I need to describe the state? Remember that the state is normalized, okay? And remember that global phase does not matter for quantum states. What matters is relative phase. Global phase is not an observable that I can actually measure. All my states are equal up to some overall phase anyway, okay? So it's 2 real parameters. You can work out this thing, yeah.
I'm sorry, I don't understand that. At which point does the copying of the state psi appear in this scheme?
At which point does the?
Copying, when does it?
When does it actually appear? I have not yet told you. I just paused here to point out that there are only a pair of classical bits that are needed, whereas if you read out, if you really measure the state and try to communicate that information, so you see a single quantum state in that sense is packing a lot more classical information through the amplitudes and phase, okay? All right, so there's another, so I use some label for this. So I call these classical bits as M1 and M2, and depending on what M1 and M2 are, now B springs into action and does some local operations in his lab, okay? And what are these local operations? They are simply x and z. So I'm going to write this as x to the m2 and z to the m1. I'm sorry, I'm using my quantum computing notation, the sigma x to the m2 and sigma z to the m1. What do I mean by raised to m2? Remember, m1 and m2 are either 0 or 1, okay? It's a single bit. So if m1 was 0, the sigma z doesn't need to be applied. If m2 was 0, the sigma x doesn't need to be applied. If both outcomes were 0, B doesn't need to do anything. And the state is here. If both outcomes are 1, B has to do both these local operations, sigma x and sigma z. And then B state becomes this unknown state. So the state has been teleported.
And the measurement happens in the Z basis?
Yes, yes. Thank you. They're all in the Z basis. So these are 0, 1 basis measurements. Yeah, absolutely. Okay, so yeah, it looks like something really strange has happened, but actually not. So let's just try to understand what's happening here. Of course, I can work out the math, right? So I can take an alpha 0 plus beta 1. I can write down this state. And remember how I did this circuit analysis? So I can analyze this circuit at every step. So write down the state here. It's a tripartite state, system of 3 qubits, which is basically psi tensor beta 0, 0. Do this, do this, do the measurement, and then you will see that this happens. That's the mathematics of it, right? And maybe you can do that in one of the tutorial sessions if someone is able to work this out and show this, that'll be nice. I don't want to spend time doing that. But what is happening? So remember, initially the entanglement was between these 2 qubits, right? This was the entangled pair. What A has done by doing this, and if you think about what these 2 operations are, they're exactly the reverse of these 2 operations. And that's not a coincidence. What this does is it actually now creates some entanglement between these 2 qubits. But now quantum entanglement is a monogamous quantity, which means if A2 is maximally entangled with B, it cannot have any entanglement with any other system. Again, hand-wavy explanation would be to say, well, I'm maximally entangled with B, which means I've exhausted all my degrees of freedom that can get correlated with any other physical system. So unless I break some of that entanglement, I cannot get entangled with another system. So this goes by the name of monogamy of entanglement. One can precisely quantify this using some measures. Maybe I have time to show concurrence in the afternoon today, then maybe tell you how this monogamy can actually be written out as a nice inequality, okay? Where you can bound for a tripartite state, how much entanglement can each bipartite component have? So that is bounded by a monogamy inequality. So what A is doing is actually, we would say, using up this entanglement, in a sense breaking this entanglement and creating some entanglement between these two. But A is not completely breaking this entanglement either, because then there is no information that gets transferred here. So you can think of this step as somehow smudging out this entanglement which existed only between A2 and B. This maximal entanglement has been sort of smudged out between these three qubits, and after doing so, A measures to collapse her pair of qubits, and because of the way these set of operations have been set up, collapsing that leaves B in a state which is the same as psi up to a local unitary transformation. Yeah.
And what is the Hadamard operator for?
So together, so maybe I should say this, so together the C0 followed by the Hadamard followed by a measurement, okay? So this whole thing, remember how we said that the Bell states form an entangled basis? And I was telling you last evening that you can, just like how you think of measuring in the standard basis, 0, 0, 0, 1, 1, 0, you can think of measuring in the entangled basis. So this circuit essentially realizes what is called a Bell basis measurement. So maybe the two-line summary of what is happening here is, in A's lab, with both the qubits at her disposal, she is doing a measurement onto the Bell basis. Her qubits, which were originally product states, are now collapsing down to one of the Bell states, okay? Because originally this unknown qubit and her half of the entangled state were in a product state. But by performing this Bell basis measurement, she's collapsing them down to one of the 4 Bell states. And by knowing which, so there are 2 classical bits here because it's one of 4 outcomes. So that's 2 classical bits, right? And by knowing which Bell basis her pair collapsed into, she just communicates that to B, and accordingly he has to do a local unitary rotation to get back psi exactly. So the key ingredient here is breaking off this entanglement and instead creating entanglement here. So by the time this complete step has happened, the entanglement between A2 and B is completely broken, and instead A1 and A2 are now in a maximally entangled state. So that's your monogamy thing, that this maximal entanglement has now completely been transferred here, right? And it's been done in such a way that what remains is actually the same as psi up to a local unitary transformation.
So after performing these operations, the bit that B has been converted to psi.
Yeah.
But we cannot know what the state is until unless this classical channel.
Yeah. So I can already show you this. So let's say that A did not communicate the measurement outcome. So then this has not happened. So what does B have? B could have one of 4 states. B could have psi itself, or a state which is actually psi up to a sigma z, or a state which is psi up to sigma x, or a state which is psi up to sigma y basically, right? X times z is y. So B then is actually in a mixture, is in a classical mixture of these 4 states.
Yeah. So my question is, we say that it is not information is not transferring more than the speed of light because we have to do it by classical
So there are, yeah, okay, so I'll again try to answer this, but yeah, it is true. So I'm not saying that there is no discomfort or that there is nothing non-local happening, all right? But to be able to read out this quantum state finally, or even to be able to realize this quantum state. So let's say A did not do the measurement at all, and A not doing the measurement, or even A doing the measurement and not revealing the outcome, is basically like doing a partial trace. Mathematically, it's as if you're doing a partial trace of the first 2 qubits here of the 3 qubit state. And remember, we did this partial trace operation yesterday also. So if you trace out 2 of the 3 qubits, you're going to be left with a single qubit state. That single qubit state will now be in a mixed state. Okay? Because you do not know what happened in this measurement process. Okay? Even if you assume that the state has been realized here, until and unless these local operations have been done, you're really not in this state. Like I said, you're in one of these 4 states. So even to claim that your teleportation protocol is complete, you need to have done these local unitaries. So yeah, so without this classical communication, you cannot do this. So yeah, I mean, I've just given you I'm not showing you the math. It's just, again, linear algebra bracket jugglery. So I encourage you to try and do this. Yeah.
But is there a way to formally show that a classical communication channel is always necessary?
Indeed, you can write down the tripartite state here. This is some state, right? Psi A1, A2, B.
No, I don't mean for this scheme specifically, but in general, to like reproduce states, you need a classical communication channel.
Okay, so how would you otherwise reproduce a quantum state? So let me turn the question back to you. So like I said, one is to measure, and I already said, you measure, you get classical information out. Now, you can ask me, can you not do a unitary, fully unitary transformation which reproduces the quantum state for me? And I'm going to come to that next, so maybe this is a good point to mention. So can I not have a quantum Xerox machine which can copy a quantum state, an arbitrary quantum state? The answer, it turns out, is no. So interestingly, quantum information allows you to do fancy things like teleportation, but the simplest of tasks, which one does all the time with classical information, copying, is not something that you can do with arbitrary quantum states. Okay? So quick, have people seen this no cloning theorem? Yes? Everyone knows this? Some of you. So maybe I'll just quickly talk about this. Yeah. Yeah?
This whole teleportation, like algorithm or whatever, is this a unitary operation?
Up until here, it's a unitary operation. As a whole, it is not, because there is a measurement involved. There is a measurement involved. And there is, in a sense, there's breaking of superposition, there's breaking of entanglement, right? So you have consumed one entangled state, which in itself should tell you that it's not a unitary transformation. You started out with one entangled state and 1 qubit, 3 qubits in total. You're finally left with only 1 qubit and 2 classical bits, right? So it is a non-unitary process. So the point is that, can I not think of doing this? So there is some unknown state in A. Let's say that B is initialized to some fixed state. Okay, you can think of this as the blank sheet that you put in a Xerox machine. Can I not, in some unitary way, end up with this? Okay, and the answer is no. And again, there's a simple way to show this. The point is, I can design a unitary operation for specific sets of states. If you tell me that the state that I'm going to put in the box is always 0 or 1, or maybe it's always plus or minus, right? In particular, if you tell me that it's one of a set of orthogonal states, then I can prepare a unitary operation. This is sometimes called a quantum cloning machine, okay, fancy words, if you like, which can then do this for you. which can make a copy of this state here. But if it's going to be an arbitrary cube, even a single qubit state, then it is not possible to realize this transformation, psi tensor 0 going to psi tensor psi, in a unitary fashion. Okay? So this is this famous result due to Wouters and Zurek, much before quantum information became a very fancy thing to do, but this is called the no cloning theorem. Yeah, let me just say this here. Oops. Yeah.
But why do we require the condition for this operation to be unitary? So not every operation that we can do with quantum statistical.
Yeah. So subsequently, people looked at, can you do this in a non-unitary way, right? But how do you realize a non-unitary transformation? Once your operation becomes non-unitary, you should realize that it becomes probabilistic in some way. It becomes a stochastic operation in some way, right? Because a non-unitary operation is irreversible. So one way to think about a non-unitary operation is it is actually a unitary on an extended system. So you can attach some additional quantum systems and make it unitary. But then this process itself becomes probabilistic. So there's now a probability of failure of your cloning device. Okay? So if you want to do deterministic copying of quantum information, you cannot do that. Yeah.
In context of monogamy of entanglement, what we can tell of the G is that states, because there are G qubit entanglement.
So I was not in the afternoon. We'll talk about GHZ in the afternoon. Yeah.
So in the earlier example that you had here, that the C naught created the entanglement.
Mm-hmm.
It was created after that, there was nothing.
There was superposition.
There was superposition,
Yeah.
but there was no entanglement before.
Yeah. Yeah.
So the entanglement content actually changed.
Mm-hmm.
Here the C naught gate is not changing it, it's just transferring it from one bit to another.
Yeah. Yeah.
Can you say something?
Well, here you already have the entanglement. Like I said, the C naught plus Hadamard is acting together like a projection onto a Bell state. So if you just think about the C naught is just acting in A's lab, and it has at the end of this, the states, the pair of qubits in A's lab are in an entangled state. So it has created entanglement in that sense, except that it has consumed some entanglement in doing so, right? And it has made use of this entanglement to create this, right? And therefore, there is some information transfer that has happened. If this was not at all in the picture, right, this is still like an entanglement creation circuit. You have basically projected whatever state here into one of a set of 4 entangled states.
So you're saying that this monogamy statement that you made earlier, that is a separate thing?
Yeah, that's a separate thing. I'm just saying that A cannot simply hope to entangle this maximally entangled state with her qubit. That is not possible. That has to be broken for this entanglement to happen.
Does it mean, if I understand you right, that at the end of this process, B, which was in a pure state before, is now in a mixed state until I get a telephone message
Yeah,
and
yeah,
apply
absolutely.
unitary
Yeah,
transformation?
yeah.
So, and then, getting this extra information, I turn it from a mixed state to a pure state.
So, by the way, B was in a mixed state to begin with, because B was entangled with one state in A's lab. That is the initial state. So B was in a mixed state. It is just this state which was in a pure state, this unknown state in a box, that has become mixed because some entanglement has been created in this process here. So this state has become mixed, but B state was always mixed. In fact, B state has at the end become a pure state. And you can think of this purity as having been transferred here. If you wish to, I guess that was your, yeah.
B0 was the pure state.
Together with A, it's a pure state. The state in B's subsystem alone, to begin with, is not a pure state. It's a maximally mixed state. Together with A2, it's a pure entangled state. This was a pure state to begin with, but that has become mixed in this process. Okay? Okay, I did not expect this to take this long, but maybe it's good to have questions. Okay, so let me say that what I have shown you without really doing the algebra is that you can indeed do this. So you use up one E bit, which is basically one entangled state, two classical bits to communicate one qubit worth of information. So today, of course, teleportation has been realized over very large distances, maybe again including space, satellites and whatnot. All it requires is for these two spatially separated labs to have access to a pair of entangled photons. And then they do these local transformations and they can demonstrate teleportation, right? It's not just a fancy tool, it turns out it's very useful even in quantum computation setting, where you may want to transport a state exactly from one end of a quantum circuit to another somehow, right? And maybe you have these parts of the circuit being mediated by photons or something. So then you can use an entangled photon pair to transport a state from one part to another while preserving the superposition in the state. That is the crucial part. What was alpha 0 plus beta 1 here remains alpha 0 plus beta 1 here. You have preserved the coherence in the state in doing this entire process, right? Okay, so this is one kind of resource statement that you can do using entanglement. Now there's another kind of resource statement that you can do, which is, suppose somehow communicating qubits was easier and communicating classical bits was harder. Don't ask me in which world that happens, but suppose we enter that era where qubits are easily communicated, but classical bits are not. Then you can do something called super dense coding. I just want to mention that as well. Before I stop, I think I'll have to stop with this today probably. So now, again, it's a kind of communication scheme between these two parties. Once again, they share, okay, so let me not start like this. So in this scheme, the situation is slightly different. So I'm going to draw a single line to say that there is a quantum communication channel. Okay? No more cell phones and WhatsApps and all that, but it's now a quantum communication channel. But they don't have a classical communication channel between them. They only have a quantum communication channel. And A, in her lab, prepares this entangled pair. Okay? This is some entangled state. So maybe it is one of these Bell states, right? So this is a Bell state. So the idea of this protocol is that by using one entangled state and by communicating one qubit over this channel, they effectively can communicate two classical bits of information. Okay, it's a kind of reverse of the teleportation scheme where they used the entanglement along with classical bits to communicate one quantum bit. But here they are using one quantum bit along with the entangled pair to realize two classical bits. And this is a nice thing to see because it tells you something about the local unitary aspect of the Bell states, right? Yeah.
So quantum communication channel is something which can transmit a state.
It can transmit a quantum state, exactly.
It will be like teleportation.
It need not be like teleportation.
What is
How else? It's basically how would I, for example, transmit a single photon over a fiber optics?
You're saying just physically.
Just physically. It's a fiber optics channel, right? And let's say it's polarization maintaining, it's very nice, there is no noise, etc. So whatever polarization state of the photon you prepare, it's going to travel as long as you want, right? It's an ideal quantum communication channel. So that's what one means by, yeah. Okay, so how would you do this? So now both the qubits are first sitting in A's lab, and let's say that now A wants to communicate two classical bits, which means it's a binary string, right? It's a string with two bits. So what are the set of all 2-bit strings? There is 0, 1, 1, 0, 1, 1, 0, 0, right? And how would, so now the question is, how is A going to encode these 2 classical bits into her entangled state? So she's going to find a way to do that and then send across the entangled state to B. So, yeah, I'm sorry, maybe I should have, yeah. Okay, so let me say that, okay. So A has, all right, so they have this quantum communication channel and they share this entangled pair. So that's what I wanted to say. I'm sorry. Okay, so, all right, I should have backed up a little bit. So I shouldn't have said both parts of the entangled state are in A is what I said, which is not quite correct. So let's say the picture is sort of identical to this. Each half of the entangled state is in each person's lab, except they don't have these 2 lines classical communication channel. They have this quantum communication channel. So now the point is, A can only apply local unitaries on her half of the entangled state. Okay? So I hope the idea is clear. Someone, let's say, has already distributed this entanglement to them. So each one has one half of this bipartite state. Now A can only perform local unitary operations on her part. By performing local unitary operations on her part and sending across that qubit, she is going to basically communicate one of these 4-bit strings to B. Okay? So maybe I'll write this down and then it becomes clear what this is. Of course, the unitaries that she's going to do are exactly like this. It's exactly the reverse of the teleportation scheme. So maybe you already see what is happening. But let's say that the state they shared to begin with is beta 0, 0. So maybe I'll work this out here. Okay, let me do this here. So I'm going to say what happens if you apply one of these 4 unitaries to beta 0, 0. So A could do nothing, which is just identity, right? And that is just beta 0, 0. Let's say A applies a sigma X operation on this maximally entangled state. So that's a local unitary. You realize that the zeros and ones basically get flipped. So this gives you the state 1, 0 plus 0, 1 by root 2. A applies sigma Z. That changes a phase. So that gives me 1, 0 minus 0, 1 by root 2. Then A applies both X and Z. So that is both. So that becomes, so the sigma X makes this, what do I want to say? Oh, sorry, this is just a, yeah, I already jumped the gun. So this is just 0, 0 minus 1, 1. A sigma Z here does nothing to the first 0, 0, right? It only flips the relative phase here. So this is 1, 0 minus 0, 1 by root 2. So the point is that by applying one of these 4 operators, which is simply a Pauli or the identity, A has converted their joint entangled state, which was originally in this Bell state, into one of these 4 states. Okay? So without having access to the second qubit, just with access to one half of the entangled state, she has steered this joint state into one of these 4 states. Now, for this information to fully reach B, so there's 2 bits of information encoded in this set of 4 states, except B now has access to only one half of this. So by communicating the other qubit that she had so far, after doing this local unitary transformation, B now has access to this full entangled state. Now B just has to do this Bell basis measurement, as one has been talking about, to distinguish one of these 4 states, and then B gets one of these 4 classical strings. Is the idea clear? So this is so-called super dense coding. So it tells you that if you have access to entanglement and a quantum communication channel, then maybe you can somehow compress information in different ways, right? And this is the simplest example. There's much more complicated things about entanglement assisted quantum communication and things like that, but this is the simplest protocol you can think of, where you're communicating classical information and encoding it in a more compact way perhaps by doing this, okay? And it also tells you this power of local operations, okay? In both of these protocols, you have shared an entangled state, but you have manipulated it purely using what are called local operations and classical communication. So this is one powerful paradigm in quantum information processing. It's called LOCC, local operations and classical communication, which cannot change the entanglement content overall. But it gives you a way of manipulating entanglement and maybe transmitting information in various ways. So maybe I should stop here. It's not wise to start something, but questions? LOQC. So that in a sense is the problem of quantum communication channels itself, right? So you can think of super dense coding as doing something like that, right? But, yeah. You don't. You now collapse it back into a product state. Remember that when you do the Bell basis measurement, you finally get one of these 4 outcomes. So you don't have the state as such. Yeah. You can think about that. Yeah. Yeah, you had a question.
Right to say that without an entanglement period, we can never communicate an arbitrary thing, arbitrary state. Because we need arbitrary large number of bits, structural bits to.
So the question is, do you have, see, if you have access to an ideal quantum communication channel, okay, which is an idealization, then indeed you can communicate that, right? So it's a question of what you assume as what you have access to. So if you have access to only a classical communication channel, which is how I pose this problem, then you cannot, without entanglement, communicate this, right? Or communicate this perfectly the way you do this in the teleportation protocol. In the teleportation protocol, it is deterministic. You do a measurement in between, but conditioned on that outcome, you're doing some unitaries. So if I look at this whole box, it's deterministic, right? There's nothing probabilistic about it. I will get this state in the end once I do all these steps. So that you cannot otherwise have. The only thing that will mimic it is an ideal quantum communication channel. So that's why Abhishek was asking, what do you mean? Is this what you mean? So this is in a sense an ideal quantum communication channel, right? Yeah.
Will the trying to communicate a maximally entangled state also lead to these same states or?
What do you mean by communicating a maximally entangled state? Send both parts. A maximally entangled state always has 2 parts to it. There's a subsystem A and a B, right? So in this protocol, what you're doing is somebody has, like I said, already distributed these 2 pairs to these 2 labs, okay? Finally, what A has to do is only send 1/2 of that to B. So what A is sending is only 1 qubit, finally. But you're assuming that they have this, what we call pre-shared entanglement between A and B. Okay? All right, so we'll meet in the afternoon and I'll talk a little bit about mixed state entanglement, which will also lead us to multi-party entanglement. Somebody asked me about GHZ and all that, so we'll cover as much of that as we can. Yeah.
entanglement content for any general like density matrix or like?
So people have different
qubits,
measures. For
yeah.
qubits, yeah.
Qubits, yeah.
Negativity is a measure, subsystem Farnham and entropy is a measure.
Yeah.